So welcome everybody. It's my great pleasure today to introduce Gary Froyland. Gary received his PhD in 1997 from University of Western Australia, where he worked under the supervision of Alistair Iain Mees. These days, he's a professor in the School of Mathematics and Statistics at UNSW in Sydney. He has research interests in the fields of dynamical systems, ergodic theory, discrete optimization. He's an expert in transfer operator methods and applications to geophysical fluid flow, oceanography, and atmospheric science. His work on optimization has had important impacts on international mining operations, cancer, radiation therapy, to name only a few. And we're just delighted to have him join us today. And thank you, Gary. And it's all yours.
Thanks, Jay. Thank you for the invitation, and thank you for the alternate time today to fit in with my strange location. So I gave Jay a couple of titles, and this is the one he picked. So I hope it's good. So this is joint work with Harry Crimmins, who's a recent former PhD student of mine. And yeah, well, I'm talking about statistical limit laws, so and their approximation. I guess that's where it fits in with the seminar, maybe. And stability, I'm going to use as a kind of general term to mean stable under perturbation. So I'll start with the kind of dynamics that we're going to consider. So we have some dynamical system. It's going to generate statistics, and one of the simplest test beds of dynamical systems are piecewise expanding maps of the interval. And so here's an example of one of those. You've got piecewise branches. This is your unit interval, which is your domain. And the branches don't have to be onto the domain. And in fact, in this simple case where you're piecewise affine and you don't have onto branches, if you plot histograms of long trajectories, then the density, first of all, you know there is a density with respect to the Lebesgue, but that density can be complicated, like what you see here on the right. So this is the domain again, this is 0, 1, and this is the density. So the average density should be 1, so the average is through here, and some parts are lower density, some parts are higher density. I didn't do this by computing a normal, but I did it by a rigorous numerical method, maybe not rigorous in your sense, but at least a converging numerical method. Even in these areas that are looking flat, there is still some fine structure there. So you get already complicated phenomena even just in the distribution of long orbits. So these are still non-trivial maps. We're going to look at 1D maps. We're also going to look at expanding maps in higher dimensions, although it's not sure we're going to look at it. Our theory covers this case, but I'm not going to look at those today. The other type of map I want to look at are uniformly hyperbolic maps. So you don't just have all directions expanding, but now you have some directions expanding, some directions contracting. And the classical test bed here are called Anosov diffeomorphisms. And this is maybe the most well-known of those. This is a linear automorphism of the two torus, known as Arnold's cat map. And so if you flatten the torus to a square, okay, so you identify the left and the right sides and the upper and lower sides because you've got a torus. If you apply the linear map to this square, then you get this parallelogram. And because you're on a torus, you're doing all the computation mod 1. So these pieces all fit nicely back in together to the torus, and you get a nice smooth map of the torus. If you run a long trajectory, here this has 150,000 points, you get a distribution like this. And this should be distributed according to Lebesgue measure, and that looks like that is the case. And it doesn't really matter where you start. So Lebesgue, almost all initial conditions have trajectories distributed according to Lebesgue. Now, if we perturb this a little by adding some periodic nonlinear terms, you're still on the Anosov class, but you don't preserve Lebesgue anymore. Instead, a long orbit now looks like this. So you have some clear variation in the density. But again, the picture you get is independent of initial conditions. So there's a classic theorem from the late 60s and early 70s. If you've got a C2 transitive Anosov diffeo, like we have here, then there's a unique SRB, Sinai-Ruel-Bowen measure, that describes the long-term distribution of trajectories for Lebesgue almost all points. And yeah, one more thing about the structure of this measure. So this is not absolutely continuous anymore, but if you condition on unstable manifolds, which are these stripes that you see here, if you condition the measure on those stripes, then you do get an absolutely continuous measure. All right, so those are the three types of dynamics that our theory is going to apply to. So let me now talk about the main tool I'm going to use, called the transfer operator. So, okay, some notation. So X is going to be my phase space. This is either an interval or in higher dimensions, some compact subset of RD, or the 2 torus. And in cases 1 and 2, we'll be having expanding dynamics. And in case 3, we have hyperbolic dynamics. So on X, we want to define a Banach space of functions. This is going to be where our transfer operator is going to act. In the Inosov case, they're actually distributions, they're not functions. They're complex valued, and exactly what B is will depend on the setting. So in this first part of the talk, I'm just kind of sketching ideas rather than going into details. So the transfer operator, in this third case, where you have a diffeomorphism, you're invertible, your dynamics is invertible, you have this simple formula for the transfer operator. It's simply composition with the inverse of the map. That means you're a push forward on functions under the dynamics. And then you have the scale factor, which is just coming from change of variables under T, change of variables in integration. And the reason you have this is so that the Lebesgue integral of a function is preserved under the action of L. So if F is a density, when you push it forward, you want it to be a density again, and so you have to rescale by this Jacobian factor. In cases 1 and 2, you're expanding, so you're in general many to 1, and so it's the same deal, but you just have to sum over all the pre-images, which can be a finite or countable set. Okay, now we're going to be using the spectrum of this linear operator a lot. So again, just to sketch what we're going to need. The map T and the B, we're going to need to match them so that you have what's called a spectral gap. So your spectrum is going to sit inside the unit disk in the complex plane. You want to have the eigenvalue 1 as your leading eigenvalue. And by leading, I'm going to mean that it's the only eigenvalue on the unit circle, and the rest of the spectrum is strictly away from the unit circle. So a cartoon might look like this. Maybe you have some isolated eigenvalues, and then you have the rest of the spectrum, which is called the essential spectrum. So if you have this this setup here, you're what's called quasi-compact. Quasi because, I mean, if you were compact, then this essential spectrum would be just the origin. And with quasi-compact, you're allowed to blow up the origin to some non-trivial neighborhood of the origin. So the fact that your transfer operator is quasi-compact in the 1D expanding case, that is, I guess, what I'd call by now classical, due to Keller in the early 80s. And a decade or so later, this quasi-compactness was shown for multi-D expanding maps. And then we had to wait quite a while to get to the Inosov case. But this was the first paper, Blank, Keller, Liverani, who finally built a Banach space for hyperbolic maps. And since then, people have got super interested in this again, and there's a whole suite of different exotic spaces that work for different types of hyperbolic maps. All right, so that's the maps I'm looking at. That's a sketch of the transfer operator. And now I want to get onto statistical laws, which is mainly what I'm talking about today. So one of the most well-known is the central limit theorem. And classically, that says that if you've got independent, identically distributed random variables, mean 0, variance sigma squared, and you combine them weighted according to root n, then this random variable converges in distribution to a normal random variable. And we want to make a deterministic version of this. So we will create an observation function. This is just something we're going to use as our dynamical system runs on its phase space. At every point in our trajectory, we're going to create an observation, a number, and we're going to combine them like this along a trajectory. So what I'm effectively doing is up here, I'm defining new random variables with yn is our observation observed n steps in the future according to our deterministic dynamics. And by now it's well known that if t is, I mean, I've written here sufficiently chaotic, but this, I mean, you could think of this in terms of quasi-compactness, but there are other ways of thinking about this. Basically, the correlations between each of these observations should decay sufficiently rapidly, and if that occurs, then you get a central limit theorem. This sum here, which I'm calling Sn, or later I'll refer to as a Birkhoff sum, this random variable converges in distribution to a normal random variable. So as I mentioned, you can prove this in several ways. A really nice way, from my point of view, is to do this spectrally. And even spectral approaches for the CLT have been around for quite a while. And these days, people are looking more at the case where the T's can change from step to step. So that's the sequential case. Or the T's are driven by some ergodic or stochastic process. That's the random case. And yeah, I have with some collaborators, we've proven the existence of the CLT, the local CLT, and a rate function for the expanding and hyperbolic cases. Okay, so just to illustrate this with some pictures and an example, here's an observation function on my torus. Okay, so my torus is here, and these are the outputs of my function. So, okay, what does the central limit theorem say? It says that this Sn on root n, this random variable, converges in distribution to a normal. So just to illustrate that, we need a distribution. And so here I'm distributing 10,000 points in a square in my torus. This is my torus. And here's my G. So G ranges from values -2 to 2. And I chose this square to be somewhere near the minimum. So you, on the right, you see a histogram of the values of G for these 10,000 points. And they're all clustered around the minimum -2. So this is very non-normal. And as I let the movie run, I'm plotting on the left where that square goes in the phase space. So you can see it's very quickly mixed through the phase space. And on the right, I'm plotting the histogram of Sn over root n, which you can see in a couple of steps gets from very non-normal to something that looks reasonably normal. So this is just an illustration, so brute force illustration of the central, of what we're talking about here with the central limit theorem. So one thing you can do, and people have been interested in recently, is to try to rigorously numerically estimate the variance of this normal distribution for a specific map and a specific observation function. And here are the recent works. So these two middle ones, they're looking at expanding either circle maps or full branch interval maps, which are simpler than what I've shown you here. These guys are doing piecewise interval maps, so of the same complexity that we have. And in what I'm going to talk about, we can do these also in multi-D and in the hyperbolic case. And we're also going to talk about other perturbations, not just numerical. And we can also do the rate function, which I'm coming to shortly. Okay, so on this slide, I want to sketch how you prove the classical CL, sorry, not the classical one, how you prove the deterministic CLT using transfer operators. So you're going to need what is called a twisted transfer operator. So you make this new operator with a complex twist. So Z is just a complex number. And you define this by, you use your original operator, but first you multiply your argument by e to the zg. So g is the observation, z is a complex number. And the reason you do this is because powers of Lz encode the Birkhoff sums of G. So if you take the nth power of Lz acting on F, then this is the same as the untwisted operator acting on e to the z Sn, this Birkhoff sum of G's F. And we need to get this Birkhoff sum in there because that's what we want to. We want to talk about the statistics of the Birkhoff sum. So this is a convenient way of getting it in there. We're also going to need that Lz has a spectral gap for small z, and that the dependence of Lz on z is differentiable. So the way you prove this spectrally is through characteristic functions. So by the Levy continuity theorem, if you have a sequence of random variables converging in distribution to another random variable, that is equivalent to the characteristic function of the sequence converging pointwise to the characteristic function of the limit point. And so this is the path we're going to take. So the characteristic function of this is just this. So recall characteristic functions are just really Fourier transforms where you switch the sign in the Fourier transform. Okay, and now if I want to get over to here, I want to switch my mu, which is my invariant measure, with Lebesgue. So I'm going to put in this compensating d mu de Lebesgue term. And then we're going to recall that the transfer operator preserves Lebesgue measure. So I can stick in here as many powers of L as I like because it preserves Lebesgue measure, and I place in there n copies. All right. Now I look at this. What do I have? I have L to the n e to the something Sn, and that looks very much like what I have up here. So I say, oh, this is just Lz, where z is it over root n. That is my twist. So it's t is real, I is imaginary. So this is a pure imaginary twist. N powers of that. Now we're going to use the fact we have a spectral gap. So the spectral gap means that we have some leading eigenvalue that's just sitting out there by itself. And so the question is, how fast does this grow? And it's going to grow like the leading eigenvalue to the n plus other eigenvalues that are going to grow at much lower rates. So asymptotically, we're looking like this. And now what I want to do is use this third property, the differentiability, to Taylor expand in the twist. So my about zero. So my first term is lambda 0. This is my first order Taylor term. This is my second order Taylor term, and so on. And then for reasons that are not obvious, but also not difficult, it turns out that this first derivative is 0. It's essentially because our observation has mean 0. So that this will go away. And what we're left with is lambda naught, which is 1. Okay, that's the spectral radius was 1 for the untwisted operator. We have this term again, and then we have other terms which again you can show go away. And when you take the limit, so this is the first year, if you ignore these, then this is first year analysis to show that this goes to this. And now you look at this and you say, oh, this is the characteristic function of a normal. And not only that, you know what the variance is. The variance goes here. So that we've identified the variance as the second derivative of the untwisted leading eigenvalue at twist 0. And that's a sketch proof of how you prove the CLT using these twisted transfer operators. And it's not a long argument, and you get to identify what the variance is. Okay, so that was CLT. So now on to large deviation and rate function. So the CLT, you can view this as talking about medium or moderate deviations from the mean. And if you want to look at large deviations, if you want to look at tail probabilities, then one way of doing this is through what's called a large deviation principle. So Birkhoff, or if you like, the law of large numbers, says that if you compute averages of your observation along a trajectory, then you converge almost surely to the mean. But you can ask, well, suppose I don't take the limit. Suppose I just go to some finite n, and I ask, how big is the set of initial conditions so that if I compute trajectories of length n, I deviate from the mean by more than some threshold s. So how likely is this? How unlucky can I get with my initial conditions? And so the way you measure how unlucky you are is to take the measure of this set. So here, this is what I'm doing here. I'm taking the measure of this set. And it's well known for, well, 30 years now that in the deterministic case, this measure decays exponentially quickly in n. So it gets exponentially unlikely to pick one of these bad initial conditions. But how fast that exponential decay occurs, that is a function of the threshold that you choose. And so what you can do is you can take the measure of this set, and then to get that exponential rate, you take logs, divide by n, and take a limit. And for each s, you're going to get a number. And when you put all these numbers together, you get a nice, well-defined function, which is called the rate function. So this rate function describes for each threshold s, what is the rate at which this exponential decay occurs. And okay, so let me indicate this again in an example. It's the same observation function as before. Let me go back to the picture of it to remind you what it looked like. So I'm going to choose a threshold of 1/2. So that's up here. And if I cut through the graph at 1/2, then you basically get these yellow areas. So these yellow areas are where the function exceeds the value 1/2. So now if I go back to my movie, in the first frame, the blue is where the function exceeds 1/2. So I'm going to, in my illustration here, I'm choosing a threshold 1/2. As I let this run, I'm plotting on the left the set where the Birkhoff sum exceeds the mean by a threshold s on average. And this set should decay exponentially fast in size. It doesn't maybe really look like that. It looks like it for the first few iterates, but then finite pixel size kicks in. But if you plot a log of the measure of this set versus orbit length, then you see you get a straight line slope. And this straight line slope is the value of the rate function evaluated at 1/2. So if I repeated the experiment with something else instead of a half, like a quarter, let's say, then I'd get a different slope here. All right, so we're going to numerically estimate this rate function spectrally. All right, so now I'll go into a little more detail about how we do things. So my B is going to be a complex Banach space. LB is going to be all bounded linear operators, and I'm just going to call one of these A. So A is going to be either our transfer operator or a twisted transfer operator or a perturbation or a perturbed twisted transfer operator, one of those. Okay, so the spectrum is, as usual, sigma of A. Spectral radius is rho A. The essential spectral radius is rho S. And we're going to, so quasi-compact, we had that cartoon picture before, and the important thing about the one leading eigenvalue on the spectral radius, this is what I'm saying here. This is just a long-winded way of saying that there's only one eigenvalue on the circle of radius, the spectral radius. So in that case, you can write A in this eigen decomposition. So you have lambda, the top eigenvalue, times pi, so some rank 1 eigen projection onto the corresponding eigenspace. And then you just have the rest. So we're just peeling off the top eigenspace. So in this setting, it's classical, like Kato type arguments, that if you've got a simple quasi-compact operator of this, so simple quasi-compact operator, that means that this, you can write it like this. And you've got A prime that is close enough to A in operator norm, then A prime is also a simple quasi-compact operator, and its leading eigenvalue is close to lambda. So there's nice, but this operator non-closeness is typically way too strong for anything you could possibly get in dynamical systems type arguments. And any numerical method would fail to satisfy that. So what we do is use an approach that's been around for 20 years now. So we introduce a weaker norm, single bar, so that the unit ball in the strong norm is compact in the topology of this weaker norm. And then we define a third norm, which is this triple bar I'm going to call triple norm. And it's defined as you see here. So you take the supremum over functions in your strong unit ball, but you evaluate the effect just in the weak norm. If this is weaker than the operator norm, the operator norm would be, this is a double bar here. Yeah, so you've weakened the operator norm to something else. And Keller and Leverani showed that if your A prime is close to A in this weaker norm, and you satisfy some natural dynamical conditions, then you get the same closeness results on the spectrum and the eigenprojections. So let me tell you what these conditions are. So suppose you have a family of operators. Think epsilon is going to be a perturbation. So this is a family of perturbed operators that in some sense are getting close to A0. So if they converge to A0 in this triple bar norm, that's the closeness condition. And then the two dynamical conditions I was talking about are written here. So I guess this doesn't mean too much. I'll come back to them a little later when we look at examples. This just says that your operator is power bounded in the weak norm. And then there's this strange looking condition, if you haven't seen it before, but it's used all the time in dynamical systems. It's called a Lasota-York inequality, or in probability a Dublin-Forte inequality. And what you want is that when you hit your function with powers of your operator, you contract geometrically in the strong norm, but you're allowed to add possibly quite large amounts in the weak norm. So if you have all these things, then you have the following theorem. So if you're quasi-compact, simple leading eigenvalue, you have this nice decomposition for the zeroth, for the unperturbed operator. And then you have a family of perturbations that satisfy the three conditions above. Then the top eigenvalue of the perturbed operator converges to the unperturbed one. And the same thing for the this rank one projection and the remainder operator, all in the triple norm. So that's all very nice. Okay, so the parameter epsilon, that corresponds to our perturbation. And for us, this can be stochastic, deterministic, or numerical. We're going to need to introduce the twist I talked about before. And we're going to need, I mean, you can see how, when I talked about CLT and how that ran, I needed two derivatives. So we're also going to need stability of derivatives of eigenvalues with respect to the twist. Okay, so formally, what is a twist? A twist is going to be an operator. It takes as argument a complex number, and we need that it has analytic dependence on Z, and zero twist is doing nothing. And we'll say that this is compactly weak bounded if for every compact subset of your complex domain that you're interested in, you're uniformly bounded in the weak norm. And so maybe don't worry too much about that, because the main example we're going to use is just multiplication by e to the zg. So m of z acting on some f is just f times e to the zg. And g is going to be bounded, so it's kind of clear how this is going to be satisfied. All right, so this is our new main perturbation theorem. So what we're doing here is we're augmenting the Keller-Leverani setup to include twists and derivatives with respect to the twist. So we've got a quasi-compact operator. It has a simple leading eigenvalue, and it's got its usual decomposition. And then we have these perturbations. And now we're making perturbed twisted operators. So we take the perturbed operator and we twist it. So this A epsilon might be some numerical estimate of the transfer operator, and we are now applying a twist to that. So if Z is small enough and our perturbation is small enough, then our perturbed twisted operator also has this, this quasi-compact decomposition, simple quasi-compact decomposition. And all of these, the top eigenvalue, the perturbed top eigenvalue depends analytically on Z. Similarly, the projections. Now what happens as epsilon goes to 0? As epsilon goes to 0, the derivative of all orders of the top perturbed eigenvalue converges, so this is a function of Z, this converges uniformly to the nth derivative of the unperturbed eigenvalue, which is also a function of Z. So this is uniform in Z. The uniformity here is in Z. Yeah? The uniformity is not in particular, okay, let me just say uniformity is in Z. That's the easiest way to say it. And the same is true for the projections. So this is what we're going to need for our perturbation theory. Let me try and explain how this works in examples now. So suppose you've got a piecewise C2 expanding covering interval map. So covering means if you take a little interval, then in a finite number of iterates, you'll expand over the whole interval. So this is what's going to give us the unique leading eigenvalue. It's like a mixing condition. What is B? Okay, so B is going to be the space of functions of bounded variation. And this is classical. So this goes back, 30, 40 years. This is the standard thing people use for these kind of maps. The norm, the strong norm, is going to be the variation of the function plus its L1 norm. And the weak norm is going to be just the L1 norm. So it's clear here how this is weaker than this one. And it has the nice property that this unit ball is compact when you embed it in L1. So perturbations. The perturbations can be of numerical type. So how we would construct a numerical approximation of our transfer operator is we would post-compose our transfer operator with some finite rank projection. And it doesn't matter, I guess, too much. I mean, there's nothing, you just have to satisfy the conditions in our theory for the, whatever you choose for your projection. What I'm going to use in this case, in this piecewise case, either 1D or multi-D, we use what's called Ulam projection because this works nicely with variation. So how this works is you've got your unit interval, you break it up into, let's say, 1,000 little subintervals, and you have some function f that you want to project. And so what you do is you make a step function on these 1,000 intervals, and the height of the step is just the expectation of f restricted to that subinterval. So it's just the kind of obvious piecewise constant approximation of a function that you would make given a partition, given a finite partition. Okay, and our perturbations can also be of stochastic type. So if you have a stochastic kernel, K epsilon, converging weakly to a delta, then you convolve and you get some perturbed transfer operator. And I mean, you can think of, dynamically, you can think of this as you apply the map and then you add some noise, and then you run the map again and you add some noise. So dynamically, that's what this would represent. All the perturbations can be of deterministic type, where you perturb the map. So now you have your map, but then maybe you move the branches around a bit to make some different map. And as long as this, I'm not saying exactly what this metric is, but it basically measures the distance between branches. If that is small enough, then you'll get the L epsilon that comes from the T epsilon being close to the L that you had for T. Okay. So each of the above conditions, each of the above perturbations satisfy the closeness condition. That's that's some effort sometimes to show, but you can show that. Each of the perturbations gives you a Markov L epsilon Markov, meaning that the perturbed operator still preserves Lebesgue integration. This projection pi epsilon preserves Lebesgue integration, convolving with a stochastic kernel preserves Lebesgue integration, and just choosing a different map, well, you also get a transfer operator preserving Lebesgue. So actually, condition 2, which was this one, this is Lebesgue, this is the L1 norm. So if you take powers of a Markov operator on the right-hand side, you can just put 1. So the K1 can be 1, C1 can be 1. So that's trivial in this case. And condition 3, that was about the Lasota-York inequality. Because we're using variation, because numeric perturbations of the type we're using reduce the variance, you have some function, you make a step function out of it, that's going to reduce the variance of the function. And stochastic convolution also reduces the variance of the function. So you pretty quickly get condition 3, because that was about the variation, linking the variation of iterates under the transfer operator to the original variation. So all these things can be verified pretty easily in the 1D case. In the multi-D case, there's quite a bit more work to do. In fact, we don't use bounded variation, we use quasi-Hilda norms from a paper by Sassol in 2000. And, but now we have all these conditions, we can apply our main abstract perturbation theorem, and that's going to tell us that we get uniform convergence of the derivatives of all orders of our twisted eigenvalues. All right, so how do we actually compute the variance in the rate function? So my CLT argument I gave you near the beginning of the talk, I argued that the variance was given by the second derivative of the top eigenvalue with respect to the twist at 0 twist. You could, I guess, if numerically, you could compute the top eigenvalue for twists nearby 0, and you could do differencing to try and estimate this second derivative. But I think a better way, a more reliable way, is to use this formula, which is well known, has been around a long time in linear response and related fields. And everything you need here is you have. So you have the G, the V is the eigenvector of the lambda. I mean, not differentiated lambda. And the L is your operator. So everything here is you have, there are no derivatives, and this is a much more reliable way to compute things. The rate function, for not obvious reasons, but I can't, I guess, explain everything in this talk. It's given by a convex conjugate expression. So this is very standard when people do rate functions. This is convex. I mean, in order for this to apply, you have to show that log lambda is a convex function anyway. So that's something you have to prove. But once you have that, then you know the rate function is given by this. So this is some optimization we're going to have to do, but it's a convex optimization. So this is a corollary, I guess, of our main abstract theorem, specifically applied now to these piecewise expanding maps. So you've got a usual thing, piecewise expanding covering interval map. You've got your perturbations. G is your observation. It's going to be in BV because that's our Banach space now. The mean should be 0. This is a co-boundary condition to say that you're not degenerate. If this were 0, then when you make your Birkhoff sum, you get something trivial. All right, then what happens as epsilon goes to 0? So if you compute for each epsilon using this formula, say, the second derivative of the top eigenvalue of your perturbed transfer operator at twist 0, then as epsilon goes to 0, these converge to the true value, the unperturbed value. And second, for the rate function, if you compute the value of the rate of your perturbed rate function using this formula, which is just where I had before, except there's an epsilon here, then when you send epsilon to 0, you get uniform in S convergence to the true rate function. Okay. Okay, so here are some numerics. This is the map I had before. Now, on the right, I've got 4 different observation functions because I want to try and emphasize the meaning of the variance and the rate function. So in the purple, I have this step function from left to right, and the others are kind of weaker variants of this. So the yellow is also has this kind of left-right flavor, the red a little less so, and then the blue is kind of the opposite. The blue is really symmetric left to right. It's not odd. The reason I'm doing this is because of the dynamics here. So if you initialize a point in 0, 1/2, then it's very likely that you remain after one iterate in 0, 1/2. In fact, the only way you can escape is if you're near 1/4, and then you see this tip here just pokes a little bit above 1/2. So if I were here at my next iterate, I would land just a little to the right of 1/2. And then I would start circulating around the other half. So the dynamics here is going to be, typically you spend a long time here, and then occasionally you switch over here. So if I were observing with the purple function, and I initialized here, what I would see is values 1, 1, 1, 1, 1, 1, and then at some point I would switch and then get a sequence of -1, -1, -1, -1, and so on. So you have these long sequences of similar values followed by a switch. And in that case, the variance, you'd expect the variance in your CLT be very large. As compared to the blue, where it's kind of the other extreme, you don't observe this asymmetry at all, and you'd expect a smaller variance there. So what we do is, we use Ulam, we're using equipartitions of the interval for n up to 25,000, and for each n, we compute the top, we compute this using this formula. This is just the nth Ulam based estimate of the transfer operator. This is the leading eigenvector, and G is your observation. So this is all pretty easy to compute. We don't compute the inverse, of course. We compute the action of the inverse by solving a linear system. Okay, so here is an indication of the variance estimate. So you can see this was the blue, this was the symmetric observation, and this was my step function. So you can see there's a massive difference in the variance. This is small, this is very large. This kind of gives an indication of the kind of convergence that you observe for different numbers of Ulam subintervals. Okay, for the rate function, what we do is for each S, we numerically estimate our nth version of the rate function by solving numerically this, we optimize numerically this convex function. So we minimize this convex function. We don't do anything fancy. We just use MATLAB's built-in quasi-Newton unconstrained routine. It takes like 5 to 6 iterations to get a pretty good accuracy. And when we move on to the next S value, we seed it with the optimum for the previous one. So this further speeds up the computation. So here are the observation functions again. And on the right, this is my rate function. The rate function has to, notice that the maximum value these functions take is 1. So if I were to extend this threshold out to 1, the rate functions all have to diverge to infinity. So, and in fact, once you get to about 0.8, you start to run into some numerical issues. It gets more and more difficult to converge. And that's because you're getting close to this place where the functions have to diverge. But again, you see this big difference between the blue and the purple. So what the purple being small, this means that you have a reasonably high probability of exceeding the threshold for long sequences for large n, because you have these long chains of plus or minus 1. The blue, on the other hand, you get a lot more mixing of values, and so you have a much smaller, remember this is e to the minus whatever value, the probability is e to the minus whatever value you see in the rate function here. So these values here, the probability in the blue case is much smaller that you experience these large deviations for long periods of time. All right. Yeah, these are just some error comparisons. So these are four pictures of 4 different rate functions. I'm just comparing yellow for different subintervals. So yellow is 200, red is 1,000, blue is 5,000, all relative to, I don't know what the real answer is, so all relative to the largest resolution we used. And you can see that, of course, blue is better than red is better than yellow, and the errors get worse as you push further along toward this maximum threshold of 1. All right, no, I don't know how much, can someone tell me how much time I have, if any?
Yeah, I guess 5 minutes.
5 minutes, okay, then let me quickly say something about null-sort maps. Yeah, so all the examples I showed you were for the 1D case. Let me say a little about the null-sort maps, which was our second paper. So here you need a different norm. You need an anisotropic norm because you want to treat the unstable and stable directions differently. So we're using this, what was developed in this follow-up paper by Quasicompactness and Ladrani to this initial paper. So they have these norms, PQ norms, P and Q integer. And how this works is in the unstable direction, you're differentiating some CR function P times. So this is penalizing how smooth you are in the unstable direction. In the stable direction, the index Q, it's the order of differentiability of a test function against which you integrate. So this is like a smoothing effect. So you have this anisotropy in your norm. And if you want to make a weaker norm, what you can do is you can increase the order of differentiability of your test function. So you can increase the Q, and you can decrease the number of times you differentiate in the unstable direction. So there's an easy way to make a weaker norm. And so this pair is like, this is like BV, and this is like L1 that we had before. This is the strong and this is the weak. Right, so to make your B, your BPQ, you complete CR functions with respect to this norm. This space is contained in the space of distributions of order R. You have the compact embedding of the strong unit ball in the weaker space. You can get a Lasota-York inequality in this pair, just as we had for BV and L1. And you can show your quasi-compact. So just to be concrete, a minimal setup could be P is Q is 1. R here could be 3. And your map then should be C4. So it has to be 1 more than P plus Q. And I guess let me just focus on, so what this very last point here is, so what we can show is stability of the SRB measure that I talked about right at the beginning of the talk. And again, the variance and the rate function for our numerical schemes. What are our numerical schemes? Because we're on a periodic domain and we have a smooth map, Ulam is not necessarily a great thing, and in fact we can't prove anything for Ulam. So we're using Fourier approximation because this is much more natural. I mean, it preserves the smoothness and it's periodic. So there are 2 approaches that we use. One is we first convolve our twisted operator with some stochastic kernel, and this is efficient because this is just convolution is multiplication in frequency space. And then we just project by Fourier truncation to obtain our finite rank approximate twisted operator. The second approach is nicer, I think. So what we do there is we convolve with a Fayet kernel. And so these Fayet kernels, they have explicit Fourier coefficients. And so actually what you're doing is you're not doing a standard Fourier truncation. You're truncating, but it's a weighted truncation. And so you take the coefficients that you get from the truncation and you combine them according to what is prescribed by the Fayet kernel. So that is nice. This is like a 1-step method. And with both methods, you don't need to know anything about the geometry in the phase space. So we're not adapting this to the stable and unstable directions. These are just completely standard, you know, Fourier in the X direction and Fourier in the Y direction. Okay, I've got two theorems. Let me just quickly, they're both essentially the same. So the results are very familiar to what you've seen. We've got our observation function. It's not in BV anymore. Now it's in CR. It has zero mean. This is some condition, some translation condition we need on the norms, which is technical. But for large N, for large resolution, and for a small twist, we get that the approximate twisted operator is quasi-compact and has a simple leading eigenvalue, and that eigenvalue depends analytically on Z. So it's the same as we had before. The SRB measure is stable in the sense that if you were to compute the top eigenvector of your approximation, it converges in the weaker of the two norms to the true SRB measure. The variance is stable in the sense that we had before. So if you take the limit as your resolution goes to infinity of this second derivative of the approximate eigenvalue at zero twist, that goes to the real variance. And the rate function is stable. So if you compute an approximate rate function at resolution n, that converges uniformly to the true rate function as the resolution goes to infinity. And how we prove this, it's the same abstract theory as before. We now have some Anosov specific theories. So essentially all you have to do is check that you satisfy these KL conditions, because now you're in you have a new Banach space, you have a new type of map, you have to check these conditions again. But I mean, I would say this is it's a positive for the approach, because you just have to go back and check these conditions which have nothing to do with twists. So these are all untwisted. There is quite a bit of work to do with the specific setting we have, and also with the type of Fourier approximation. We need different arguments for the two different methods, but you can check this. And I've used my 5 minutes, I think. So let me just quickly flash up some pictures. What we're doing here is we're using 128 Fourier modes in each direction. So that's 2 to the 14 in total. This is our estimate of the SRB measure, which, if you squint, looks, I mean, the dark and the light is matching what you see on the right here. If you look at this in 3D, you see you have nice, smooth, I said you're absolutely continuous in unstable directions, and you see here, by theory predicts you should be smooth in these directions, and you are. Of course, you should be rough in the orthogonal directions here, but there's a limit to how much roughness you can get, because this is some linear combination of 2 to the 14 complex exponentials. So you're simply limited by how irregular you can be. Just for fun, I did Ulam on 2 to the 18 grid cells. And so you look at this compared to this and you say, wow, this is fantastic. It's so high resolution. But if you look at what is really going on here, you have, it's not very smooth at all in the unstable directions. And we can't prove anything about this estimate either. So yeah, I think I'll this is my last slide. This is a computation of the rate function for the Anosov map, and the observation function we had here. Remember, it's between -2 and 2 in value. So again, as you get up to 2, these should diverge to infinity. And this is a comparison of the highest resolution versus the next lowest resolution. So you can do well for low thresholds, but errors increase as you increase the threshold. All right, thank you for listening.
All right, thanks a lot, Gary. Very nice. Does anyone have any questions?
Hi. Yeah, I had a question. This is a beautiful talk. I'm biased. I like statistical properties of the kind of dynamical systems you were talking about. So my question's very naive. So the core of the argument is this Keller-Liverani heart, right? Like this before twisting, before your theorem, where you involve the twists, and you still get that all the eigendata converge nicely as epsilon goes to 0. So the question is so in that untwisted case, the KL theorem, is that like the optimal theorem, or is there like a dream theorem? So for you, coming from computing numerics for these statistical laws, is there like something better than KL before twisting? Like, or is KL for you the ultimate theorem?
No, I think KL is, I mean, there's not too much you could want. I mean, you could want, maybe you could write a quantitative version of it. So it is part, no one has bothered to do this, but if you look at the proof, it's all about estimating norms of resolvence, and one could dig into the proof and with enough information on different pieces, one could turn that into something quantitative. But otherwise, it's very satisfactory. No one's, I mean, it's heavily used in many different areas, and the big advantage is that it has this much weaker notion of convergence, which you can frequently get. And the two dynamic conditions, usually you have them anyway, because usually your transfer operator has to be quasi-compact to say anything about statistics. So the other two conditions are kind of things that you already have. So I find it very satisfactory. I would say it's, I haven't dreamt of something better apart from the quantitative side.
I see. Yeah. And follow-up question, I love that, the cartoon you had at the beginning with for the quasi-compact, you had the essential spectrum, right? And then you had these isolated things around it. So this, again, is a very naive question. Maybe it's just a stupid question, but does that essential spectrum, somehow that essential spectrum, how do I want to phrase this? Is there dynamically or statistically useful information hiding inside the essential spectrum? Because it seems that we ignore it, right? Like, big question.
I tend to ignore it. I think that, I mean, there's information in these other points here. So all I used in this talk was this one here, this eigenvalue here, and its twisted version. Yeah? Mm-hmm. But I'm also looking a lot at these other eigenvalues here. But the essential spectral radius tells you something dynamically. Well,
the rate of speed in some of the convergence, is that what you mean?
Yeah. So you can relate it to, you can relate it to, so toward the end, I skipped over this very quickly. Here. So the radius of the essential spectrum, this is in the Anosov case. Okay. So you can, in the case where we choose P and Q to be 1, then this new U, this is the expanding, this is the uniform rate of expansion, the lower bound on the expansion rate in unstable directions. So you've got this Anosov map, right? At each point in phase space, locally, you have some expansion, and locally you have some contraction. And so if you expand a lot, then this decreases the essential spectral radius. So that would be the expansion rate, 1 over the expansion rate, nu U to the -1. And nu S, if you're contracting a lot, this has the same effect in this norm. So, and in the expanding case, it's even easier. In the expanding case, the stronger the expansion, the smaller the essential spectral radius. So there is this link between the essential spectrum and the dynamics. But beyond that, I haven't seen the essential spectrum used in any way.
And these other eigenvalues, you were saying they also are interesting?
Yeah, I mean, in the untwisted case, in the untwisted case, let's say this one here is the closest to the unit circle. So then that already just describes what's called the exponential rate of decay of correlations. So if you calculate autocorrelation, the autocorrelation function, say, so that'll exponentially decay in time, and that rate of exponential decay is given exactly by this eigenvalue. Sometimes these are not here, right? So sometimes there are no dots and you just have the essential spectrum. So in that case, the radius of the essential spectrum would govern that exponential decay of correlation rate. Right. So either it's these points or the essential spectrum. You can also look at the eigenfunctions of these things. So this is something I do a lot. They tell you what are the structures that are, so you have some exponential rate of decay, and you can ask, well, what are the phase space structures that are responsible for that? There must be structures in the phase space that are actually decaying at that slow rate, and what are they? And that can tell you something about, that tells you something more about the dynamics.
Thank you.
Are there any other questions?
Can I ask something, please? Yeah.
By all means, the floor is yours.
Yeah. Yeah. So the formula for the variance, you said it comes from linear response theory, right? But I mean, so do these systems have a linear response?
Not necessarily. Well, no, probably not in general. So the dependence on epsilon. So to have a linear response, you need some kind of differentiable dependence on epsilon, on the perturbation. So if you think of epsilon as the parameter that you're changing in linear response, and Keller-Livrani doesn't say anything about it. Keller-Livrani is purely a continuity theorem, so it's not a differentiability in epsilon theorem, and so you need to do a bit more work to get that. But generally, piecewise interval maps, piecewise continuous interval, piecewise differentiable interval maps generally don't have linear response, and if you want the simplest kind of 1D map that has linear response, then you have to go to expanding maps of the circle, which is more limiting. So either expanding maps of the circle or expanding maps of high-dimensional tori or things like that. And then you can apply these, then you can apply transfer operator type ideas, but you have to use, you can't use the Keller-Livrani theory as I presented. That's just about continuity, not differentiability.
But then the formula works anyway, the one that you are using. So.
Yeah, so it's not derived, I guess, I can't remember exactly what I said. So it's used it can be used in linear response. It's not derived as a consequence of linear response. This is an old expression. I wanted to say that it's a Kramer formula, but I'm not 100% sure about that, so I didn't want to say that. It's
probably in Ruel's book, Thermodynamic Formalism. So this formula is in that book, and that book's been around for over 50 years, right? So it's
getting up to 50, yeah.
Getting up to 50, yeah.
Yeah, I'm sure it's in Ruel's book. you can derive this in the you can derive this fairly simply using, if you write down, the way we derive this in the paper is you just from conditions that the derivatives have to satisfy you. So you start off with your basic eigenconditions. So you have L of Z acting on V of Z is lambda of Z times V of Z, just the basic twisted eigenequation. And then you differentiate both sides. And then certain things have to be satisfied and you differentiate again. And then you solve your equation, you isolate this, and this is what you end up with. So it's not a very difficult derivation to find this expression just directly from the twisted eigenequation. I'm going to add that in my next version of this talk. I'll add the few lines that take you from here to here.
Okay, anyone else? Any other questions? Well, then I'd just like to say thanks again, Gary, for coming and speaking with us today.
It's my pleasure. It's a nice way to start the morning. It got me out of bed a little earlier than usual, so that's nice. I feel energized now.
Okay, great.
Thank you for hanging around.
Thank you very